Hello everyone, welcome to our music generation project for CSE 153. We worked on Task 1, Symbolic Unconditioned Generation, and Task 4, Continuous Conditioned Generation for this assignment. First, let's go over our agenda. As you can see from the slide, each task will cover starting from task introduction to music playback. We'll begin with Task 1, Symbolic Unconditioned Generation. The motivation is to model the joint distribution of a piano and violin duo. Our approach consists of three steps: event-based tokenization, an autoregressive transformer, and MIDI generation. The dataset we used is called, I'm not sure how to pronounce it correctly, but lock MIDI dataset, or it's also called LMD. Moving on to exploratory analysis, data collection, pre-processing, and discussion. Where does our dataset come from? As previously mentioned, it's from the law committee dataset compiled by Colin Raffel. You can see the dataset using the link below. How was it collected? The MIDI files were scraped from the internet and matched against the million song dataset. It covers a diverse range of genre, including pop, rock, jazz, etc. What is it for? Originally, it was created for music research, but nowadays it is widely used for tasks such as music generation, style transfer, and music transcriptions. Next, how do we process the data? First, we filtered the dataset by keeping only MIDI files that contain both piano and violin tracks, resulting in around 18,000 files. Then we converted each MIDI into an event-based token sequence using a vocabulary of 390 tokens. The train validation split was 85-15 with random seed. Finally, the dataset is constructed using a sliding window of 512 tokens, where each sample is an input target pair shift by one token. Now let's look at the data analysis. The first plot shows file duration. Most files are under 500 seconds, meaning most tracks are relatively short. Piano notes per file also follows a similar pattern, with most files having under 2,000 piano notes. Also, with the violin notes per file, it is similar with the piano. The MIDI program distribution shows that piano programs 0 to 7 and violin programs 40 to 47 is the most common, though other instruments are also present since we kept all files containing at least piano and violin. Now let's look at the data analysis. The first plot shows file duration. Most files are under 500 seconds, meaning most tracks are relatively short. Piano notes per file also follows a similar pattern, with most files having under 2,000 piano notes. Also, with the violin notes per file, it is similar with the piano. The MIDI program distribution shows that piano programs 0 to 7 and violin programs 40 to 47 is the most common, though other instruments are also present since we kept all files containing at least piano and violin. The second set of plots give us more additional insights. Looking at the pitch distribution, both piano and violin are centered around MIDI pitch 60 to 70, which corresponds to middle C and above, which is the typical range for the melodic instruments. The tempo distribution shows most tracks fall between 60 and 120 BPM, which is the standard range for most musical genres. Note duration is heavily concentrated below 0.5 seconds for both instruments, which indicates mostly they are short and detached notes. Finally, the scatter plot of piano versus violin shows that there aren't really strong correlation, and it suggests that the two instruments are very kind of independent across the files. Moving on to modeling. How did you formulate your task as an ML problem? Music generation is formulated as an autoregressive sequence modeling problem. The model learns to predict the next token given all previous tokens, formally written as the equation on the slide. The input is a sequence of 512 tokens from a vocabulary of 390, covering note on, note off, time shift, etc. events. The model is optimized by minimizing the cross entropy loss. What models are appropriate for the task? The three models, RNN, LSTM, transformers, are all viable. RNNs are simplest and the most lightweight. LSTM improves on RNN by better handling sequential dependencies. Transformers are the most powerful among the three, which is excelling at capturing long-range structure through self-attention. What are the pros and cons of each model? RNNs are computationally efficient but can suffer from vanishing gradients. LSTMs solve this problem from RNN, but it increases the complexity. Transformers require more resources, however, it provides superior context modeling and parallel processing capabilities. That's why we picked Transformer for our task. So basically, we implemented a transformer based model with multi head attention for capturing the complex musical patterns. In our implementation, we use PyTorch for model construction. The model is trained with next token prediction. The input sequence are represented as single learned token embedding combined with positional encoding. Dropout and layer normalization are applied within each transformer layer to prevent the overfitting. Now let's walk through our workbook. We implemented a music transformer class using PyTorch. The model takes a token sequence as input, passes it through a learned token embedding and a positional encoding, then through four transformer encoder layers with 8 attention heads, and a fee 4 dimension of 1024. A casual mask is applied so each position can only attend to previous tokens. Finally, a linear layer maps the output back to the vocabulary size to produce the logits. For training, we used Atom Optimizer with a warm-up and cosine deca learning rate schedule. The learning rate linearly increases for the first 1,000 steps, then cosine decays to 0 over 20,000 total steps. We also applied gradient clipping with a max norm of 1.0 to stabilize training. So as you can see, at the output, every 1,000 steps, we evaluate on validation set, and every 5,000 steps, we save a checkpoint. Also below, you can see the plot that we have implemented. Now for the generation, we use autoregressive sampling, starting from the seed of the first 100 tokens. From the training set, the model predicts one token at a time. We apply temperature scaling to control the randomness and top K filtering with K50 to avoid very unlikely tokens. The last 512 tokens are used as a context at each step. We generate 2,500 tokens in total, which are decoded back into the MIDI file. Now, the evaluation. How our task should be evaluated. We use perplexity as the primary metric, measuring how well the model predicts the held out data. What should be the properties of good output? It should be the coherent pitch patterns, realistic rhythm structure, and the balanced piano-violin interplay. What is the relationship between perplexity and musical properties? Perplexity measures the statistical fit to the data, but does not enforce harmonic rules or musical structure. So we complement this problem with adding distributional comparisons. What are the baselines? The baselines are uniform random, which is sampling uniformly over all token. The unigram, sampling proportional to the training token frequency. How do we demonstrate our model is better? Our model achieved perplexity of 8.9, which is meaningfully better than the baselines. So it means that the model has been learning the musical patterns meaningfully beyond the simple frequency statistics. Now let's walk through the evaluation code. In 9.1, we run the evaluation function on the validation batches to compute the average cross entropy loss, then convert it to perplexity using the exponential. As you can see, the model achieves validation loss of 2.1862 and the perplexity of 8.9. We can see that our model outperforms both by a large margin. In section 9.2, we generated 5,000 tokens and compare the token type distribution between real and generated music using a bar chart. So looking at the bar chart, we can check whether the model produces a realistic balance of note on, note off, time shift, velocity, and instrument tokens. And we can observe that it's quite reasonable. Finally, at 9.3, we compare pitch distributions separately for piano and violin using histogram of real versus generated notes. This tells us whether the model generates pitches in a musically realistic range for each instrument. We can observe from the graph that the piano is quite reasonable, however, the violin is quite narrow. Moving on to the discussion of related work, how has this dataset been used before? The dataset was originally created for music information retrieval research, as previously mentioned. Second, how has prior work approached similar task? Performance RNN by Google Magenta used an LSTM with event-based tokenization, the same tokenization scheme we adopted. The music transformer by Huang and al. Extended this by replacing the LSTM with transformer using relative attention. We also used the same method for our model. Lastly, how do our results compare? Direct comparison is difficult due to different datasets. However, our model achieved a perplexity of 8.9, showing that the model has genuinely learned musical patterns. Despite using a simpler architecture than the music transformer, we still achieved meaningful results, suggesting our approach is reasonable. Lastly, I'll play the first 10 to 15 seconds of our generated song.
Next, we will discuss the second part of our project. For this task, we focus on task 4, which is continuous conditioned generation. Unlike symbolic music generation, where the output is a direct sequence of notes or MIDI events, the goal here is to generate actual piano directly from a MIDI score. Our pipeline begins by converting MIDI into a piano roll representation with onset and offset information. These representations are fed into PerformanceNet, which predicts a log power spectrogram. We then reconstruct audio from that spectrogram using Griffin-Lim phase reconstruction. For training and evaluation, we use a subset of the Maestro dataset. We used 30 hours approximately of the full 200 hours, which contains professionally recorded piano performances that were captured on a Yamaha Disclavier piano. So our dataset comes from Maestro version 3.0, which is one of the most widely used benchmarks for piano synthesis. The performances were collected through the International Piano E competition using the Yamaha Desclavier pianos that we mentioned before, which record both highly quality audio and also convert it into accurate MIDI data. The full dataset contains around 200 hours of recordings, and we only trained on 30 hours due to computational limitations. And we evaluated them using separate held-out validation and test subsets of around 3 hours each. Maestro is commonly used for piano transcription, symbolic music generation, and score-to-audio synthesis. So that's why we use it for this project. For our data processing, before training, both the MIDI and audio data must be converted into representations that are suitable for this machine learning task. Each MIDI is converted into a piano roll, a binary piano roll, where each entry indicates whether a particular note is active at a given time. After that, we generate the onset-offset matrix that marks note beginnings and endings. This provides additional information about note transitions, which would be difficult to infer from piano roll alone. And for the audio recordings, we compute a log power spectrogram using the short time Fourier transform. And then finally, we align the MIDI and audio representations, divide them into separate around 5-second chunks, and store everything in HDF5 format for efficient training. And then for our data analysis, here we show an example piano roll alongside its corresponding spectrogram. The piano roll visualizes which notes are active over time, while the spectrogram shows the notes appear acoustically in the frequency domain, which illustrates the aligned correspondence that the model attempts to learn when mapping symbolic note information into realistic piano audio. And then the slide highlights examples from the process dataset that are additional. And one observation is that lower frequency notes produce strong and well defined spectral structures, while higher harmonics are more complex and challenging to model accurately. So this becomes important later on when we discuss the evaluation results, since reconstructing harmonic detail is one of the primary difficulties in score audio synthesis.
So, as for modeling, our task is MIDI to audio piano synthesis, and we can view this as a supervised regression problem. The inputs are a binary piano roll with 128 MIDI pitches over time and a separate onset and offset encoding. The target is a 1025-bin log-powered spectrogram. So, our model learns a mapping from symbolic musical information to spectrogram rather than predicting raw waveform samples directly. And thus, we choose the performance net style architecture because it was designed specifically for score to audio generation as well as piano synthesis. So, our performance net implementation has about 250 million parameters. It has a UNet style encoder and decoder, which is a type of CNN or convolutional neural network. Skip connections preserve fine timing details that could otherwise be lost during downsampling. A separate onset and offset encoder, as mentioned before, provides explicit information about node attacks and releases. Four multi-band residual blocks allow different frequency regions to specialize, helping the model present both low frequency fundamentals and higher frequency harmonics. And the trade-off, unfortunately, is that this model is pretty computationally expensive and memory intensive as well. We trained the final model on a 30-hour Maestro subset for 20 epochs using SGD with momentum on an RTX 3070 8GB. Because of GPU memory limits, our batch size was 1. We also use gradient clipping with the maximum normal 1 and learning rate scheduling. The best validation checkpoint was saved at epoch 15 with an objective of about 0.248. The final model uses soft plus outputs and a detailed MSE or mean squared error objective. So, how do we evaluate our model? A good output should follow the input MIDI accurately, correct pitches, timing, attacks, and note durations. It should also sound like a realistic piano performance with natural harmonics, clear transients, stable generation, and minimal artifacts from reconstruction. We both use objective reconstruction metrics as well as just listening evaluation. Even if we have lower spectrogram loss, it doesn't mean that the audio might sound better to the human ear because things like phase accuracy, timbre, dynamics, and well, just preference are not really optimized by this loss function. So baselines. We compare against three baselines. The first is a pretty simple sine wave synthesizer. The second is FluidSynth, which provides a strong conventional sample-based piano baseline. This does not use machine learning. And the third is this Griffin-Lin reconstruction of a ground truth spectrogram. This is used for listening only to isolate our phase reconstruction artifacts. Our learned model was evaluated on about 2100 held-out chunks, and baseline metrics were collected on smaller representative subsets to provide useful context rather than just a strict full test ranking. So let's start with the code walkthrough. So this slide summarizes the complete pipeline. Maestro provides line MIDI and piano recordings. The MIDI becomes a binary piano roll and an onset-offset matrix. Audio becomes a log power ST-FT spectrogram, which is the short time Fourier transform. PerformanceNet predicts spectrogram frames from the symbolic score features. Griffin-Lin can then reconstruct waveform audio from the predicted spectrogram. And each training sample has 860 frames, which is about 5 seconds. For MIDI preprocessing, we use Pretty MIDI to create a piano roll with the same temporal resolution as the spectrogram. Any non-zero velocity is converted to 1, which matches the PerformanceNet score convention. And because binarization removes some velocity detail, we preserve node transitions separately. A node beginning is represented by +1, a node ending by -1, and other frames by 0. And this is just showing the log power spectrogram generation. As for alignment and chunking, before chunking, MIDI and audio crop to the same frame count. The onset to offset matrix is calculated once over the complete crop piano roll and then sliced. That detail prevents sustained note crossing, a chunk boundary, from being incorrectly treated as a new attack. Silent chunks are skipped, and aligned chunks are stored incrementally in HDF5 file format for efficient loading. As for model architecture, the model passes the piano roll through 5 encoder blocks. 4 decoder blocks then upsample representation using skip connections from the encoder. The separate offset and offset encoder injects no transition features into the decoder. Finally, 4 multi-band residual blocks, as talked about before, refines frequency-specific structure from the model, or before the model produces the 1025-bin spectrogram, which is our, spectrogram result. As for training, this only happens directly in the log power spectrogram space. The code supports both ordinary MSE and detail-weighted MSE. Our final objective gives extra weight to the frequency bins 100 to 399 and to target regions containing meaningful spectral detail. This encourages stronger harmonic reconstruction. The loop also checks for non-finite losses, skips unsafe steps, clips gradients, validates the model, and saves our best checkpoint. So, evaluation metrics. Evaluation compares predictions against our held-out target spectrograms. MSE measures average square reconstruction error, and L1 is less sensitive to outliers. Log spectral distance measures the frequency level differences in decibels. Detail recall measures how often the model preserves meaningful mid-band spectral content. Here's our final test metrics. We have an MSE of 0.186, an L1 of 0.095, and a log spectral, or LSD, distance of 26.389 decibels. And this visualization here, or just spectrogram, shows like a main limitation of our model. The model captures timing and strong low frequency structures, but the mid and high frequency harmonics are kind of like way sparser than the target, unfortunately. Let's talk about inference now. The model was trained on fixed 860 frame chunks, but full MIDI files may be much longer. During inference, long files are rendered using windows with a 50% overlap. The predicted spectrogram windows are linearly crossfaded and then trimmed back to the original MIDI duration, and this reduces discontinuities between the windows. So audio output, our raw learned output, which is the performance of the spectrogram, is reconstructed with Griffin Lim. And we also made like a clearly labeled hybrid listening alternative just for better sound. FluidSynth supplies the timbre, while our learned model PerformanceNet has or imposes gain envelope derived from its spectrogram prediction. So this is just a plot showing the model-derived gain envelope that is imposed onto FluidSynth for the hybrid implementation. But yeah, for the final submitted audio, we used the PerformanceNet path, but for just the better listening alternative, we have the hybrid version. So yeah, discussion on related work. Our model follows the PerformanceNet line of scored audio synthesis, and another similar one is DDSP, which is an alternative approach that uses differentiable harmonic oscillators and noise components instead of spectrogram regression. As for where our dataset has been used before, Maestro, it has also supported piano transcription and symbolic generation research, including onsets and frames and music transformer, which are just other projects. And yeah, we'll play our song now. So now we want to replace some of our audio. I'll start with the raw PerformanceNet just from a MIDI file from the Maestro dataset, and then I'll also play the hybrid with the FluidSynth. So our PerformanceNet imposes the gain, but the FluidSynth does control stuff like timbre, so it does sound much better. So here's the raw. You can tell that was pretty noisy, so let's try the hybrid one, where PerformanceNet only controls the gain. It should be noted that FluidSynth is the traditional synthesizer approach, so it doesn't use machine learning, other than imposing PerformanceNet gain on it. And then the cool thing about our task 4 is that it does go in directly from task 1. So our task 1 generates a MIDI file, and from task 4 we can actually synthesize it so we can hear it. There was a violin instrument in task 1 though, so we had to convert it to only use piano since our Maestro dataset does not have violin, so this is going to be piano only. Well, that did sound pretty messy, so let's see what it might sound like with the hybrid variation. Yeah, so much better.